system analysis. In this lesson, we will discuss about asymmetrical fault analysis using Z-bus method for large power systems. As we had discussed in the earlier lessons, we have seen how we can use the Z-bus algorithm for solving symmetrical faults for large power systems. In this lesson, we will try to extend that method for solving for asymmetrical faults. Well, we will start with an introduction, then we will talk about Z-bus matrix formulation for sequence networks, because we know that for symmetrical faults we do the symmetrical component analysis and we get the positive, negative and 0 sequence network for the system. So, we will talk about formulating Z-bus matrix for the sequence networks. Then we will talk about how we use this Z-bus for the sequence networks for finding out or for solving the asymmetrical faults on large power systems. And finally, we will take up an example to show how this is done. Well, on completion of this lesson, you should be able to develop algorithm for building Z-bus for sequence networks. You should be able to develop algorithm for asymmetrical fault analysis using Z-bus method, and you should be able to find out the fault impedance matrix for different types of faults, and finally should be able to solve for fault currents and bus voltages for any power system for any type of fault, that means symmetrical as well as asymmetrical faults. Well, as we had discussed in the earlier lesson, when we talked about solving for symmetrical faults using the Z-bus method, here also we will consider the system under study has n buses. It is initially operating in a symmetrical normal state, that is a balanced 3-phase system state is available before the fault. All pre-fault bus voltages and power flows are assumed to be known, that is either we do a load flow analysis to get these values, or we assume that all pre-fault voltages are 1 per unit and all pre-fault currents are 0 in all the elements. Now, we will assume that the fault has occurred at a bus Q. This bus Q can be any bus in the system, and we will type of fault by means of a fault impedance matrix or a fault admittance matrix. So, this is the power system that we have, n bus power system, in which we have just extracted this bus Q, and the bus Q has A, B, C phases, and there is a fault which has occurred. This fault we are representing by a fault impedance matrix. We will see later how we do that. The voltages after fault for bus Q in phase A, B and C are represented here as VAQF, VBQF or VCQF, or we can call it as VFBQ, VFAQ and VFCQ, whatever way you want to call it. So, these are the post fault voltages. The currents flowing into the fault are IFAQ, IFBQ, IFCQ in the 3 phases. So, this is the system that we have, and we want to find out these voltages and these currents for this system when a fault occurs on the system and the type of fault is governed or governs this fault impedance matrix ZF. Now, since for a symmetrical fault we know that we do the analysis using symmetrical component transformation, that is we get into the positive, negative and 0 sequence voltages and currents, and we had seen for a balanced 3-phase system these 3 networks are independent of each other, and when a fault occurs which is an asymmetrical fault, then we find that these 3 networks do get connected by means of the fault at the fault point by means of fault impedance, and the type of connection depends on the type of fault. So, what we will do first is we will form the network for positive, negative and 0 sequence networks separately, that is we will build the Z bus for positive sequence network, negative sequence network and 0 sequence network, and finally we will assemble these 3 networks which we have developed separately for positive sequence, negative sequence and 0 sequence into a symmetrical component Z bus matrix. Now, this ZS bus, which is denoting the symmetrical component matrix, that is positive, negative and 0 sequence impedance matrix for the n bus system, will be of the order of 3n into 3n, because we have a n into n positive sequence matrix, n into n negative sequence matrix and n into n 0 sequence matrix. So, here I have shown this positive sequence matrix Z plus bus we are writing here, which is showing the positive sequence matrix. We have already seen how we can build this matrix for the positive sequence network of the system. Same way we can build this matrix for the negative sequence as well as 0 sequence. In general, the negative sequence matrix and positive sequence matrix are considered to be same, because the only elements where we find that the impedances will be somewhat different are the generators as well as the loads, where we may have been induction machine loads. Then we will find that positive and negative sequence matrix, positive and negative sequence values for these loads and generators are somewhat different, and therefore, there can be slight variation in these 2 matrices, but in general this is not large enough that will warrant a separate building of the negative sequence matrix. Therefore, in most of the time we say that positive sequence and negative sequence matrix are same, and we build only the positive sequence, we assume the negative sequence to be same. 0 sequence network of course will be quite different, because it depends very much on the path for 0 sequence currents are available or not. That is, if we have a system with star ungrounded, 0 sequence current cannot flow. So, that is an open circuit for 0 sequence currents. Similarly, if we have a delta winding, then 0 sequence current can flow in the winding, but they cannot come outside. So, which means that that winding will be shorted to the ground, showing that the current flows in the 0 sequence part, or 0 sequence current flows in the delta winding. So, we have already seen all this, how to build positive, negative and 0 sequence network for different types of connections in power system. So, we will build the 0 sequence network for the given power system, taking care of all star delta connections that we have on different sides of the transformer, as well as whether generator neutral is grounded or ungrounded. So, all these are taken care of while building the 0 sequence network. Once we have got the 0 sequence network, we build the 0 sequence Z bus for that network. Of course, since the network for positive sequence and 0 sequence are quite different, therefore, 0 sequence network or 0 sequence bus matrix or Z bus 0 is going to be quite different, and we need to build this 0 sequence Z bus. So, once we have got these, we have built these 3 sequence Z buses, that is positive sequence Z bus, negative sequence Z bus and 0 sequence Z bus, then we can assemble them together into a ZS bus, which is the sequence bus impedance matrix, where the elements of this matrix ZS11, ZS12, ZS1n and so on up to ZSNn, all these elements are basically a 3 by 3 matrix, which will include the 1 element of positive sequence impedance, 1 element of negative sequence impedance and 1 element of the 0 sequence impedance for the positive, from the positive, negative and 0 sequence Z bus matrix of the system. So, this is what this ZS ij will look like. So, any element ij of ZS bus matrix will be a 3 by 3 matrix, where we have the positive sequence element ij from the positive sequence Z bus matrix as a diagonal element placed in position 1 and the negative sequence in position 2 and as the diagonal element and 0 sequence in position 3 in the diagonal. So, this will be a 3 by 3 diagonal matrix, where the positive, negative, 0 sequence impedance values are placed as the diagonals. So, this is how the Z bus will look like, that is, we will have this n by n ZS bus, where each element of this ZS bus will be a 3 by 3 matrix. So, finally, we land with 3n into 3n matrix. The voltage and current vectors for this in the sequence terms will be given by as shown here. So, Vs bus will again be a 3n vector, that is 3n rows will be there for this, and of course, 1 column for the voltage. So, V1 Vs1 will be basically a 3:1 vector, which will be consisting of V plus 1, V minus 1 and V01. In general, the ith element of this Vs bus will be consisting of a 3:1 vector, which will be V plus I, V minus I and V0 I. Okay. So, this is how this voltage vector in sequence components will look like. Similarly, the current components will also look in the same fashion. Each element ISI will consist of the 3 elements I plus I minus I and I0I. Okay. So, this is how it will look like. Both the current and voltage vectors are now 3n vectors. Again, as we had developed the algorithm for the symmetrical faults, in the same manner we are going to develop the algorithm here. We have Vs bus is equal to Zs bus into Is bus, that is where all we have these values as sequence components there. So, these are 3n into 1 vector, 3n into 3n matrix and 3n into 1 vector. Now, from this we can write down the relationship for the ith element. So, Vsi is equal to Zsi1 into Is1 plus Zsi2 into Is2 and so on, plus Zsin into Isn. Now, these elements, as we have seen, are 3:1 vectors. So, this will basically represent 3 equations. Now, using the Thevenin's theorem, the post fault bus voltages, as we have seen earlier, can be written as Vsf bus is equal to V0s bus plus Zs bus into If S bus. That is, this is the pre-fault voltage plus the changes caused by the fault current flowing into the system, where we have already shorted all the generating sources or all the voltage sources in the system and represented them by their internal impedances. So, this we have already seen, except that now what we have here is this S coming here, which shows that we are dealing with the 3 sequence quantities for each one of them. Okay. So, the pre-fault bus voltage similarly can be written as, it is a 3n into 1 vector, where we have V plus 1 0, and since we have said that initially before fault the system is working in normal state, which means a balanced 3-phase system state. So, the negative and 0 sequence values for the voltages will be 0, and this is true for all the buses. So, we have negative and 0 sequence values for all the buses as 0, except positive sequence values, which will be having 1 per unit if we are not considering the pre-fault values, or if we have done the load flow, then the bus voltages that we get from the load flow will be put in these locations. The fault current, as we have seen earlier, is again an injection of minus ISF q at, since the fault has occurred at bus q. That is, if we go back and see this system, then only at this bus we have a fault. Since the fault current is coming out like this, which is IFS in terms of sequence currents, this fault current is coming out of the bus and going into the ground or the reference, whereas we have assumed that the fault currents or the current injections are into the bus. So, we have a negative sign associated with this, and therefore, we can see that at the qth element for this fault current bus matrix, bus vector, we have minus IFSQ term coming here, where IFSQ term is consisting of these 3 currents, IF plus Q, IF minus Q, IF 0 Q. So, each element, as we have seen, consists of all the 3 sequence values. So, the fault current is injected into the bus, which will be equal to IFSQ. So, this is what we have. Therefore, we can write the relationship for the post fault voltages using the pre fault voltages and the bus impedance matrix like this, that is Vf S1 is equal to V0 S1 minus Zs 1q If Sq. That is, if we see the relationship that we have is V is equal to Vf S bus is equal to V0 S bus plus Zs bus into If S bus. Now, If S bus, since only one element is non-zero, that is the element at qth location. So, we are getting only the qth column of Zs bus, which will be effective, because all other will be multiplied with 0 and they do not come into consideration at all. So, since all these other terms are 0 here, so all the other Z bus matrix columns will get multiplied with 0, and so they will not be coming into picture. So, what we get is only the qth column element for the Z bus. So, V0 S1 minus is coming because the current is the fault current vector at the qth element. We have the injection as minus If Sq. So, this will be V0 S1 minus Zs 1q If Sq, and so on for all the other buses. We can write this relationship. Now, let us take this at the faulted bus. The voltage, post fault voltage, is given as Vf Sq is equal to V0 Sq minus Zs Qq into If Sq. Now, we also know that at the fault bus we have the voltage Vf Sq is equal to Zfs into If Sq. That is, if we go back and see this, then the voltage at this bus is nothing but this ZF into the current which is flowing into this. So, this is what we have written. So, if the current here is ISQ which is flowing and ZF is the impedance of the fault, then we are going to get the post fault voltage as VFS is equal to ZFS into IFSQ, and this is equal to V0SQ minus ZSQQ into IFSQ. This is what we have got from here. So, this we are replacing with this term ZFS into IFSQ. So, this is the relationship that we have. From this relationship we can calculate the fault current as IFSQ is equal to ZFS plus ZSQQ inverse into VSQ0. Now, this relationship is very similar to what we had got for the symmetrical faults, except that now we have this term S coming here into picture, indicating that each term is basically a 3 by 3 matrix consisting of positive, negative and 0 sequence quantities. So, this is what we are going to get. Once we have got this IF value, then we can calculate the V value for any bus. So, VFSI is equal to V0SI minus ZSIQ into this IFSQ. So, IFSQ we are substituting here. So, for I not equal to Q, this is the relationship that we have got. For I is equal to Q, that is voltage, post fault voltage at bus Q is given by VFSQ is equal to ZFS, this term into IFSQ. So, IFSQ we have substituted here. Now, in this we know the pre-fault voltages and we know the impedances. So, we can calculate the voltages at all the buses and we can calculate the fault current also. So, this is how we try to solve for asymmetrical faults in a large power system using the Z-bus algorithm. Now, here there is only one thing, this fault impedance matrix ZFS. How do we define this matrix? We will see how we do that in the next. Now, here what I have said earlier, I have just written this down, that all relations involve 3 dimensional vectors and 3 into 3 matrices. That is, impedance elements are 3 into 3 matrices. The matrices ZSIJ are diagonal, but the matrix ZFS, which is the fault impedance matrix, is not, and this we will see how this matrix changes for different kinds of faults. In any case, all the involved matrix operations can be easily programmed on a digital computer. So, for large systems we can always write a program to solve for symmetrical as well as asymmetrical faults. Okay. The pre-fault bus voltages V0I are either obtained from load flow analysis, as I said earlier, or are usually set equal to 1 per unit. That is, if we are assuming that pre-fault currents are 0 and all voltages are 1 per unit, then we can set these values as 100. Otherwise, we use the load flow analysis to get the results for this. The positive, negative and 0 sequence bus impedance matrix can be obtained either by inversion of the corresponding bus impedance admittance matrices or by using Z-bus building algorithm. That is, as we have seen earlier, we generally prefer to use Z-bus building algorithm to trying to invert the Y-bus matrix. We will also sometimes what we do is what we call partial inversion of the Y-bus matrix, which is now preferred over building Z-bus, because for any particular fault what we need is only one column of the Z-bus matrix. that is the column corresponding to the faulted bus. So, we can generate this by using the Gauss elimination method using the Y bus for the system. So, positive negative 0 sequence Y bus we can build, and we can generate one column of this Z bus matrix corresponding to the faulted bus, and that is done by using Gauss elimination method or LDU factorization. So, instead of doing this building, sometimes we prefer that when we do not have to calculate the fault current at all the buses in the system, but if you need to calculate the fault current at all the buses in the system for fault at all the buses in the system, then it is better to build the whole Z bus matrix. Okay, so next we will talk about the how to get the fault impedance matrix, because this was the only term which we did not know about. So, let us take a general situation where we have this faulted bus Q, and at this faulted bus Q 3 phases A, B, C are there. Now, we have impedance ZA, ZB and ZC connected to these phases, and these are connected in star and then connected by means of a grounding impedance ZZ to the ground. Now, if we want to create any type of fault, we can use this kind of a system. Suppose we want to create a line to ground fault on phase A, then what we need to do is make this ZB and ZC infinity. So, these become open, and we use appropriate values of ZA and ZG to indicate the fault impedance for the single line to ground fault. If we want to make a line to line fault, then what we need to do is we will between say line to line fault between bus phase B and C, then what we need to do is make ZA as infinite and ZG as infinite and choose appropriate value for ZB and ZC. Then we have got a line to line fault between bus B and C. Similarly, if we have line to ground fault, then only ZA is made infinite and ZB, ZC and ZG are chosen proper values depending on the fault impedance that we have. So, we can create all kinds of fault using this network. Now, let us see that how we build the impedance matrix for this network. Okay. So, now we have ZA, ZB, ZC and ZG. We can always find out the admittance by taking inverse of these impedances. So, YA is 1 by ZA, YB is 1 by ZB, YC is 1 by ZC and YG is 1 by ZG. So, we can use either admittance or impedance. Now, let us write down the voltage relationship for this. Then what is VA QF? This will be equal to IAQF or IFAQ, the current flowing in this branch. So, IFAQ into ZA, this will be the voltage drop up to this point, plus the voltage drop here. This current IFNQ will be equal to sum of all these three currents. So, plus IFAQ plus IFBQ plus IFCQ into ZG. So, this is what we are going to get. So, this is what we have written here. VFAQ is equal to IFAQ ZA plus IFAQ plus IFBQ plus IFCQ into ZG. Similarly, we can write for phase B and C. So, we get this three equations for the post fault voltages of the three phases at the faulted bus. Now, this in a matrix form we can write this as VFAQ, VFBQ, VFCQ is equal to this matrix into IFAQ, IFBQ, IFCQ. And what is this matrix now? This is the fault impedance matrix in phase values. So, this is the fault impedance matrix in phase currents and in terms of phase ABC not in sequence. So, what we need to do is we need to convert it into sequence terms. So, since we are working in terms of symmetrical components, so we will change it to the positive, negative and 0 sequence terms. So, now we can write down the phase relationship V f p q, p is indicating the phasor values, is equal to Z f I f p q. This is the relationship where Z f we have already seen is what. Now, if we multiply it by the symmetrical component transformation matrix on both sides, then we have this T V f s q, that is, now we are saying V f p q is equal to T into V f s q. This is what we had seen when we talked about the symmetrical component. Similarly, I f p q can be replaced by T into I f s q. So, we have put these values here. Now, pre-multiply both sides by T inverse. So, we will get V f s q is equal to T inverse Z f into T into I f s q. Now, this term T inverse Z f into T is again a 3 by 3 matrix which we will get, and this is the symmetrical component or the fault impedance matrix in terms of symmetrical component. Now, here that is what we have written, Z f s into I f s q, where Z f s is the fault impedance matrix in terms of symmetrical component. Now, the transformation matrix T, as we have seen earlier, is given like this when we write the equations in terms of positive, negative and 0 sequence voltages and currents, and T inverse is given by this, which is basically 1/3 into the transpose of T. So, this we have already seen earlier, except that earlier we had written all the equations in terms of 0, positive, negative. We can write it in any order we want, and just to so that we can write it as positive, negative, 0 as well, we have written here as positive, negative and 0 sequence terms. So, the transformation matrix in this case will be like this. So, once we have got this T and T inverse we know, then we, after doing the multiplication, we will get the fault impedance matrix in terms of sequence values will be like this, where we have a 3 by 3 matrix Z f s given by this. Okay. Now, here these terms a square, all this, as we know, a is given by 1 angle 120 degrees. So, it is a vector which rotates any phasor by 120 degree. So, this is the fault impedance matrix that we get. Now, as we have seen, in for creating different kinds of faults, we have to make sum of these impedance Z A, Z B, Z C or Z G as infinite. If we do that, then we find that this matrix will have terms which are infinity, and therefore, this matrix will not be defined. In that case, we need to change over to a fault admittance matrix. So, this is what I have mentioned here. For some type of faults, some of the impedances take on infinite values, some elements of Z f s matrix becomes undefined. In such cases, we must work with its inverse, the symmetrical component transformed fault admittance matrix. So, instead of fault impedance matrix, we work with fault admittance matrix when fault impedance matrix is not defined, means some of the elements of this become infinite. Now, how do we find out the fault admittance matrix? We have the relationship I f s q is equal to Z f s inverse into V f s q, that is V f s q is equal to Z f s into I f s q. Therefore, we pre-multiply both sides by Z f s inverse. So, we will get I f s q is equal to Z f s inverse into V f s q, which shows that this part Z f s inverse is nothing but the fault admittance matrix YFS. And if we take this inverse of this 3 by 3 matrix, we are going to get the YFS like this. This looks somewhat complicated here, but we know all these values of YA, YB, YC as well as A, and so we can calculate this for different kinds of faults, and we will be able to get this 3 by 3 matrix for the fault. So, fault admittance matrix can be computed for any type of fault. If sometimes the fault impedance matrix is not feasible, then we use fault impedance matrix. Sometimes fault admittance impedance matrix is not feasible, then we use fault admittance matrix. So, different types of faults we have to use the appropriate fault impedance matrix or fault admittance matrix, whichever is defined for that particular fault. Okay, so, once we have got this fault admittance matrix, then we need to write the equations in terms of fault admittance matrix, and we have to compute the voltages at various post fault voltages at various buses and the fault current. So, VFSQ we can write as V0SQ minus ZSQQ into, we have IFSQ, instead of IFSQ we are writing as YFS into VFSQ. So, we are replacing IFSQ by this term, and if we do this, then we can write that VFSQ is equal to, U is the unity matrix, plus ZSQQ into YFS inverse into VSQ 0. So, this is what we will get, that is, we take this part to the left hand side and then we pre-multiply both sides by the inverse, this inverse that we will get, because we will get U plus ZSQQ into YFS into VSQF. So, we pre-multiply by U plus ZSQQ into YFS inverse, then we get this. So, this is U will be a 3 by 3 unity matrix, this is a 3 by 3 matrix, this is a 3 by 3 matrix. So, we are getting the 3 post fault voltages for the bus Q as positive sequence voltage, negative sequence voltage and 0 sequence voltages. So, once we have got this, we can calculate the fault current as IFSQ is equal to YFS into VFSQ, and VFSQ we have already calculated here. So, substituting it, we will get this value. So, if ZFS is not defined, then using YFS we can calculate the fault current like this, and once we know the fault current for the voltage at any bus VFSI can be calculated by substituting the value of fault current from here into the equation. So, V0SI VFSI is equal to V0SI minus ZSIQ into IFSQ, and IFSQ we are putting this value here. So, this is what we do. So, this is what we are going to get for I not equal to Q. Okay, I am sorry, this is I when Q is not there, this is I not equal to Q. So, this is the way we calculate all the values of post fault voltages at all the buses as well as the fault current. Once we know the post fault voltages at all the buses, we can find out the post fault currents in any branch in the system. So, this is how we try to, or we compute the post fault voltages and currents for any type of fault on a power system. So, we will take again the same example. Two synchronous machines are connected through 3-phase transformers to the transmission line as shown in the figure. The rating and the reactances of the machines and transformers are given as it was given before. Machine 1 and 2 100 MVA to 20 kV, XD double dash which is equal to X1 is equal to X2 which is equal to 12%. We are taking subtransient reactance to, so that what we are trying to do is we are trying to calculate the fault current almost immediately after the fault, and the value of x0 is 5% and xn is 4%. This is the reactance through which the generator neutral is grounded. Transformer T1 and T2, the base MVA is 100 MVA and their voltage ratios are given as 20 kV on the delta side and 400 kV. Sorry, this is not delta, this will be star. In this case we have taken both sides as star grounded, and the impedance for this is given as 8% on this voltage basis. Now we have chosen a base voltage as 345 kV, which is for the line. So we will convert the impedance for the transformer impedance positive, negative, 0 are same. So 8% impedance given at 400 kV, which will be transformed to 345 kV in per unit system. Then we get this value as around 7% or 0.07. Transmission line has a reactance of x1 x2 as 15% and the 0 sequence reactance, which is generally higher for the transmission line, is 50%. Draw each of the 3 sequence networks and find the fault current and post fault voltages for a bolted line to ground fault on bus 2 using the Z bus algorithm. So this is the system that we have. We have both the transformers which are star grounded, and we have the generators also where the neutral is grounded by means of some impedance. So this system, this is the system that we have been working on in other lessons also. So we work on this. The positive sequence network we have seen earlier is we have the voltage here, voltage source, and the positive sequence impedance is given as j 0.12, 12% impedance, xd double dash or x1, and this is transformer impedance, as we said, comes out to be 7% or 0.07. The positive sequence impedance of the transmission line is given as 0.15. Positive sequence impedance of transformer T2 is again 7%, and positive sequence impedance of the generator is again 0.12. These elements, as we have seen, we have numbered them 1, 2, 3, 4, 5, and we have already shown how to build the Z bus matrix for this. So positive and negative positive sequence matrix for this we had built in the previous class. So we will not do it again. Similarly, we will write the 0 sequence network, because positive and negative sequence values are all same in this case. So both positive sequence Z bus matrix and negative sequence Z bus matrix will be same. Now the 0 sequence, we don't have a voltage source, we have 3 xg. So xg is given as 0.04, that is 4%. So this becomes 0.12, and the 0 sequence reactance of the machine is given as 5%. So these two are in series here, connected to bus 1. Between bus 1 and 2 we have the transformer whose 0 sequence reactance is same as positive negative, which is 0.07. The line, I am sorry, this should read 50, because the line has, as we have shown here, the line has x0 is 50%, not 15%. So that should read 50. This is a mistake here, it should read 50. So J50, this has been taken care in the building algorithm. So that Z0 bus is okay. Here only there is a mistake in writing this, 1 should not have been there, it is J.5, and the T2 has a reactance 0.07. Similarly, for the generator 3xg, that is J.12, and x0, that is 0.5. Now these are the elements that we have. Element number 1 consisting of these two, element number 2, 3, 4 and 5. We can use this in the same way and build the 0 sequence impedance matrix. So positive sequence impedance matrix, which we had built in the previous class, is shown here, and in the similar way we can build the 0 sequence matrix, which comes out to be like this. Okay. So we have built both the positive and 0 sequence bus impedance matrices. Now we will see how we will use them for a single line to ground fault at bus 2. Now, for single line to ground fault, ZB is equal to ZC is infinity. That is, we have seen earlier ZB and ZC will be infinity, these are open, only phase A is grounded through ZA and ZG. So, ZB, ZC is infinities, therefore, YB, YC is equal to 0, ZG we have made equal to 0. So, YG is equal to infinity, that is, the fault has occurred only with impedance ZA. ZA is equal to ZF, and therefore, YA is equal to 1 by ZF, which is we are defining as YF. Since YG is infinity, YFS reduces to this value. That is, if you recall this matrix, now here you have YG and in all this we have YG. So, what we can do is we can divide this by YG, then this we will have YA plus YB plus YC divided by YG plus 1. So, this whole term becomes 1 by 1, and because YG is infinite, so this term will come out to be 0. So, this whole term will come out to be 1, and this YG will not be there because we have already taken it out and divided here. So, this is what we are going to get. So, the matrix reduces like this, okay, and upon substitution of YA is equal to YF and YB is equal to YC is equal to 0, if we substitute here, then this matrix YFS simplifies to YF by 3 and 1 1 1 1 1 1 1 1 1. So, single line to ground fault, this is the sequence fault impedance matrix that we get. Once we have got this fault impedance matrix like this, then we can calculate the post fault voltage at the faulted bus like this, where we are assuming the pre fault voltages to be 1 per unit, because we haven't been given any pre fault bus pre fault bus voltages from load flow. So, we are assuming it to be 1 per unit. So, we will have this we have this relationship here as VF SQ is equal to U plus Z SQQ into YF S inverse into VSQ 0. I am sorry, I made this mistake. This is U. So, we have a unity matrix here plus Z SQQ. So, Z SQQ is 3 by 3 matrix here into YF by 3 into this. So, this is YFS matrix, this inverse into VQ 0 0 0 0, because the pre fault voltages negative and 0 sequence are 0 and only the positive sequence value is here. So, if we simplify this, we are going to get VFSQ as VQ 0 divided by 1 plus YF by 3 into Z plus QQ plus Z minus QQ plus Z 0 QQ term coming here, multiplied by this 1 plus YF by 3 Z minus QQ plus Z 0 QQ minus Z minus QQ into YF by 3 minus Z 0 QQ into YF by 3. So, this is what we are going to get in for the post fault voltage at the faulted bus. And similarly, we can get the current IFSQ as YFS into VFSQ. Since VFSQ we have already seen how the relationship. So, substituting it, we will get this relationship. So, the post fault voltages for buses other than the faulted one are obtained as VSIF is equal to VSI 0 minus ZSIQ into IFSQ, and IFSQ we can calculate like this. So, if we want to do that, this comes out to be this is the pre fault voltage for that bus I minus ZSIQ into IFSQ, and substituting for IFSQ we will get this relationship for fault post fault voltage at bus I. So, this is what we are going to get for ZF is equal to 0, the above quantities, since we are assuming ZF to be 0, that is the bolted fault, we are the above equation will simplify like this. So, IFSQ is equal to VFS into VFSQ, which comes out to be this much. So, we have got VFSI in terms of Z's like this. Since the short circuit occurs at bus 2, so Q is equal to 2. So, ZSQQ is equal to ZS22, which is equal to this positive negative 0. The values are seen from the positive negative 0 sequence matrices that we have calculated. 0 sequence Z22 is this, and positive sequence Z22 is this. So, we use these values. Here we get this like this, and then we can calculate VFS2 as from by substituting all the values. This comes out to be like this, and using VFS2 we can calculate IFS2 as this one. So, we have got the values, I am sorry, this should be IFS2. So, this is the value that we will get for the fault current positive negative 0 sequence. Now, we can transform it into the phase values. If we want similarly, if we want to calculate the values currents flowing in different branches, we can use ZS12, ZS32 and all that for calculating the values at different branches. So, and for finding out the values of post fault voltages at different buses, we can use this relationship. So, again this is V0 S1 minus this relationship that we had got there. So, this is the sequence values that we have got. Similarly, for 3 and 4 also we will get the values by substituting the values from the impedance matrix and the fault current that we have calculated. We will get these sequence values. Once we have got the sequence values, we can transform them to get the phase values. So, this is how we can calculate the fault current and the post fault voltages at all the buses, and knowing the impedances of the lines or the other equipments, we can find out the fault current flowing through each element of the system. So, with this we have completed our short circuit analysis or the analysis of a faulted power system, where we have considered both the symmetrical faults, asymmetrical faults for small systems by using the sequence network or using the Z bus algorithm and Y bus algorithm for large systems. So, with this we finished today, and we will talk about the power system stability in the next lessons. Thank you very much. Welcome to lesson 33 on power system analysis. In this lesson, we will discuss the stability of power system when it is subjected to disturbances. We will start with an introduction to the problem of stability. Then we will go into the classification of different types of stability in case of power systems. And finally, we will try to develop the dynamic equation for synchronous machines in the power system. On the completion of this lesson, you should be able to explain the concepts of power system stability. You should be able to classify stability problem into different types based on the phenomena under consideration, and you should be able to develop dynamic equation of motion for the synchronous machines. Well, as we all know, power system in its normal operating state works as a synchronous system. That is, all the machines in the power system are synchronized with each other. That is, they run at a common frequency. As we have talked about in our earlier lessons, when we dealt with short circuits, we had seen that short circuits or faults create a condition which is very different from the normal operating condition, in terms that a short circuit will make very heavy currents flow in the circuit, as well as the voltages at different parts of the system will go to very low values. These are abnormal operating conditions. So a fault does create a disturbance in the power system operation, and due to these disturbances, will the power system remain in synchronism or not is the kind of study that we would be taking up in power system stability. So it says power system stability is the ability of an electric power system for a given initial operating condition to regain a state of operating equilibrium. That is, to regain a state of operating equilibrium, which means where the real and reactive power balance is maintained. That is, the system is working in synchronism and the voltages at various points in the system are within the normal operating limits. So, to regain a state of operating equilibrium after being subjected to a physical disturbance. So all this we are saying after the system has been subjected to a disturbance, whether there is going to be, that is, system is going to regain a state of operating equilibrium or not, with most system variables bounded. That is, the frequency, the voltage, all these are within the limits. None of these are exceeding or keep on increasing all the time, so that practically the entire system remains intact, which again says that most of the part or the major part of the system still remains intact, works in synchronism with voltages within normal limits. That is, a normal operating condition for the system is maintained even after the disturbance. Then we call the system is stable. So with this we will end today. Thank you. In the next class we will talk more about this equation of rotor dynamics, and we will talk about how we work with multi-machine systems, how we write the swing equation for each machine. Thank you.